right, so our first speaker needs no introduction, but I'll give him one anyway. So Ian Wanless from Monash University, and he's going to talk about some really non-associative quasigroups. Over to you, Ian.
Thanks, John, and I'll start by acknowledging the Wurundjeri people of the Kulin Nations, who are the traditional owners of the land from which I'm talking. This is a joint work with Aleš Tropal, who's from Charles University in Prague. And I'd also like to thank the organisers for putting on what promises to be a very interesting program. Lots of very interesting talks coming up after this one. And thanks for the honour of kicking the whole show off. Okay, so I am talking about quasigroups, and that's more or less the same if you're a combinatorialist as talking about Latin squares. So if you write down a finite group as a Cayley table, then it's been known since Cayley's time that what you get. Okay, so let's go back to the top of the talk. All right, so if you write down a Cayley table of a group, you get a Latin square. But if you take a Latin square and interpret that as an operation table for a binary operation, then the algebraic object you get is a quasigroup. And quasigroups satisfy these cancellation laws that you can cancel on the left or on the right. But in general, they don't satisfy the associative law, which is this one. And that's the main thing that makes a group, I guess. So there's lots of interesting work on quasigroups which are nearly groups in that they satisfy some weakened version of this associative law, and so you can look at things which are nearly groups. What I'm doing today is going to the other extreme and looking at things which are as far away as possible from satisfying this associative law. So how badly can this law fail is the basic motivating question. And to that end, I will define a quasigroup to be maximally non-associative if the only triples that satisfy this associative law are the triples where all the elements are equal. And such quasigroups were originally studied for their application in cryptography. So quasigroups are used in stream ciphers and hash functions and things. And there was a particular problem to do with second pre-image resistant hash functions, which I don't want to go into, which motivated the study of these objects. So here is the smallest example of a maximally non-associative quasigroup. And there's a little asterisk on the smallest there to remind me that I'm actually telling a little lie, because obviously if you think about the trivial group, the one element group, then it will satisfy the definition I just gave you, but I'm going to accuse it of not playing fair. It doesn't seem right for an associative object to be maximally non-associative, so I'm going to legislate that we're only looking at order 2 and above, and if that's the case, then this is the smallest example of a maximally non-associative quasigroup. So I invite you all to choose some triple of elements and multiply them in the different orders and with the different bracketings rather, and check that you get different answers unless you chose triples where all of the elements were equal. And it's obvious that in this particular quasigroup, it's idempotent, meaning that x times x is always x. And for that reason, you will have associative triples x, x, x. And my claim is that no other triple is associative in this case. Okay, so let's justify the name. Am I being too generous here? Could I do better than having those n associative triples? Because I have n triples x, 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 all of which are associative. Could I have actually done better? Well, turned out no, and the easy way to see that is to realize that for any element I like in my quasigroup, there'll be an element that multiplies on the left and on the right separately, which preserve this element x. And if you take then the triple AXB and multiply it with the different bracketings, then you'll end up with x regardless of which bracketing you chose, and hence the triple AXB will be associative, where A and X are the solutions to these equations and X was arbitrary. So for every one of the quasi-group elements, you'll have a triple with it in the middle, and that means you have at least n associative triples. And by pushing this sort of reasoning a little bit further, it's a bit more work, but Groszek and Horak showed that any quasi-group of order n will always have 2n minus the number of idempotent elements, that many associative triples. And what that means is, of course, well, we know from the above that you can't have fewer than n associative triples, but what this actually tells you is that you can't even achieve n associative triples unless every element of your quasi-group is idempotent. So that justifies using the name maximally non-associative quasi-groups for the case when all the elements are idempotent, those are the associative triples. So Groszek and Horak were studying these things from a cryptographic point of view, and they actually conjectured they don't exist. So they proved some properties and they got close to achieving the bound, but they didn't manage to achieve it. And they had tried a little bit to achieve it and decided it wasn't possible. It wasn't until actually quite recently that an example was published. So my co-author and I think one of his students did a computer search, found that the smallest example is the one that I gave you. And in fact, that's the only example of order 10 or less. But then Alice teamed up with Peter Lisnik and found a construction for these quasi-groups, an infinite family of them for odd primes to an even power, as well as one example of even order. And Peter Lisnik then went and generalized that and found examples for all sufficiently large prime powers, all sufficiently large odd prime powers, and half of the even prime powers. And I should point out that the product of the normal direct product of any two maximally non-associative quasi-groups is also maximally non-associative quasi-groups. So as soon as you have these sorts of results, you get a whole bunch of other orders by taking products of orders that you already know about. So there was this burst of papers that came out in 2020. Our paper nearly came out in 2020, but we'd been actually racing Peter. We had the same sort of ideas going at the same time. He managed to win the application race, but that was partly because we pushed to try and get a slightly stronger result, and this is what we ended up getting. So this is a theorem that I want to tell you about today. So what we can show is that these maximally non-associative quasi-groups exist for all orders, well, only 9 and up, because we know everything below that doesn't exist, with a bunch of possible exceptions here, just some sporadic cases, and then 2 infinite families, twice a prime, and twice the product of 2 similarly sized primes. So these are reasonably sparse families that we can't manage to construct with our method. I don't believe that these will actually be genuine exceptions, but there are, well, sorry, 2 times 5 is a genuine exception. We know that from this paper. So there are some small exceptions, we know that, but my guess is that they exist for all large orders. We just can't manage to quite nail these families. Okay, so as I said, you can take the direct product of any 2 examples, you'll get another one. That's a trivial observation. We managed to find a less trivial product theorem, which was one of the keys to us getting a stronger result than Lisnik did. And here is our product construction. So you take a product but only one of your factors need to be maximally non-associative. The other can be any idempotent quasi-group you like, as long as it's smaller than the maximally non-associative quasi-group you're taking. So you have those two binary operations, and you introduce a third binary operation, which is a abelian group structure on your maximally non-associative quasi-group. You stitch those things together in this appropriate way, and I don't need to tell you too much about it, but there is a way to put these ingredients together to get a product construction, to get a larger maximally non-associative quasi-group. The important thing to realize about this is that you can use here for this ingredient, you can use any idempotent quasi-group, which means you have all orders except order 2 available to you. It's kind of annoying that there is no example of order 2, and that's the reason that we get the exceptions cropping up in our theorem with that factor of 2, which prevents us using this construction in those cases. Okay, so that's the product results. What are the sort of ingredients we use to feed into that product result? Well, I need to tell you our main construction for a maximally non-associative quasi-group, and these use things called quadratic orthomorphisms. So I need to tell you what that is. So we work over a finite field of odd order. An orthomorphism of such a field is a permutation of the elements of the field such that when you subtract the identity permutation, you get another permutation. So that's the definition of an orthomorphism. And I'll give you a quick example in the field of 13 elements. So here is my orthomorphism. It's a permutation of the elements. When I subtract this line from this line, I get this, which is, again, a permutation of the elements. And that's all fine and dandy. That makes it an orthomorphism. To see why it's a quadratic orthomorphism, I'm going to calculate theta of x on x. So divide theta of x by x and ignore the fact that I'm dividing 0 by 0 in the first column. In all the other columns, you see I get either a 2 or a 5. And you peer at that a little bit longer and you realize that I'm getting a 2 for all the quadratic residues and a 5 for all the quadratic non-residues. So the way that I've designed this orthomorphism is by doubling all the residues and multiplying all the non-residues by 5. And this is what I mean by the quadratic orthomorphism. So these are the things that we use for building our quasi-groups. So again, this is the quadratic orthomorphism. You have two field elements, A and B, multiply squares by A, non-squares by B. That's your orthomorphism. And then you build the quasi-group using this rule here. So it's a very simple rule that involves applying this orthomorphism to y minus x and adding x. So that's the definition of QAB, and that's an object that turns out to be extremely useful for constructing the maximally non-associative quasi-group that we're trying to build. Just a couple of technical requirements. Obviously, I need the field to be odd characteristic to be hoping to deal with these squares and non-squares. And the other condition I need is the product AB and A minus 1 times B minus 1. They both need to be non-zero squares, or else this doesn't give you a quasi-group. And that's an easy condition. But we'll assume that all of those things are true for the rest of the talk. Okay, so I gave you the first maximally non-associative quasi-group. Here is the the smallest one that's built from a quadratic orthomorphism. It has the orthomorphism I gave you in the first row here, because if you think about substituting 0 in here, you see that you're just taking theta of y. So this first row is my quadratic orthomorphism, and this quasi-group has a very nice automorphism, which allows you to build the rest of the table from that first row. If you have a look at all of the diagonals here, they are occurring in cyclic order, and this is called the diagonally cyclic Latin square. It's a very useful structure, and because quadratic things should come in pairs, talk after this will also be dealing with these quadratic orthomorphisms and the squares that are generated with it. And that will be my honor student, Jack, who's managed to use these to solve a completely different problem. Okay, so turns out that these are very good at building maximally non-associative quasigroups. I guess the way to think about this is you've got, in the associativity equation, you've got 4 instances of the multiplication. For each of those, there's 2 cases depending on whether you're in your orthomorphism, whether you're looking at a residue or non-residue. So you basically get 16 cases to look at, and you just have to make sure that those 16 cases all work out to violate the associativity, and you churn and you churn and you churn, and you find that the that is the smallest example. You find that the conditions that will give you a maximally non-associative quasigroup, if you start with a quadratic orthomorphism on A and B, are these. So it's not particularly pretty, but you can do it. It looks like you've got 10 conditions. Actually, you get down to the bottom and you realize you've got 18, because you go through 1 to 9 and then you go through them again with A and B interchanged. But pretty much all of your conditions are this thing, are about quadratic characters of certain field elements, where the elements are polynomials in A and B, and they get a little bit messy, but that's basically all that's going on here. And that's because in the associativity equation, you have these 16 cases to deal with that may or may not lead to some coincidence with the left-hand side being equal to the right-hand side. And in order to avoid those coincidences, you need all of these things to be true. So crank the handle and you get a pretty messy case analysis, but this is what you end up with. So that is the conditions under which a quadratic orthomorphism will give you a maximally non-associative quasigroup. It's then possible to use standard arguments with wild bounds to show that these conditions are satisfied in all large fields. So we know that there are small fields where they don't work, and it turns out that before too long, these are giving you, I should say, this is large fields of odd characteristic. So that's one of the ingredients we needed, but there's a bunch of things that we don't get from the construction because of the requirement for the fields to not be too small. We know that there are not examples of order 3, 5, 7, or well, possibly not 11. So it's useful to have products of those orders. So you can define orthomorphisms in groups as well as in fields. You can't do the same pretty games with quadratic residues and non-residues, but you can still hope to find the things you're looking for. And indeed we did in these particular groups, which gave us a whole bunch of the starting cases for our constructions. So the things we weren't able to build were these. I suspect, well, possibly 11, maybe 12 and 15 might be exceptions. I suspect these are not genuine exceptions. They just didn't fit our construction. And likewise, only for small primes, I think, will these actually be exceptions. So that was what we did in our first paper. That was the one that was published this year. We have a follow-up paper which is submitted, and in that we look at the proportion of quadratic orthomorphisms that give you maximally non-associative quasigroups. So obviously you have a whole bunch of things which need to be residues or non-residues and whatever. So that explains why we're getting large powers of 2 here. But but if you crunch through all of the different cases, we worked out that the asymptotic proportion of quadratic orthomorphisms that work are these constants 1 mod 4 and 3 mod 4 behave a bit differently. But the key point here is that it's asymptotic to a constant fraction of all quadratic orthomorphisms that will work. So that will give you a lot of examples. And in particular, if you were interested in the cryptography, which I'm not particularly, you might want a large random example of one of these beasts. And this theorem shows that you've got a good chance of finding one just by choosing values of A and B and testing whether they work until you find a pair that does. And it's very simple to do that because we've got the conditions that you need to be true, which you can evaluate fairly quickly. And this shows that you've got at least a 1% chance of that working for any given large prime. And so that's quite nice for the cryptography application. Okay, so that's my talk. The first paper, the first theorem is in this paper published in Algebraic Combinatorics, which came out this year, and we have a follow-up on the archive that gives that theorem from the previous slide. Okay, that's me done.